Okay, up to now we have discussed the different model, AC analysis model, that means the RE model, H parameter model, high bit pi model for the analysis of the transistor in different configuration, common emitter configuration, common base configuration, or the common collector configuration. Okay, and calculate the different parameter related like that, voltage gain, overall voltage gain, current gain, overall current gain, input resistance, output resistance, like that. Okay, that will be these all the parameters are useful related to the amplifier. Now today onwards we will discuss the frequency response, so that is a very important topic. So today onwards we will discuss the frequency response of the amplifier. That means whenever we discuss the amplifier, first we draw the response, then we will understand what do you mean by that. That means suppose in the y axis we plot the gain and the x axis we plot the frequency in hertz, and obviously this is also in log scale, not the general scale, it is in log scale. Okay, so now this is curve is something look like this, this is not exactly the correct, but something like this. Here this is your maximum gain, 1 minute, this is your maximum gain, this is your 3 dB. Okay, so this is your 3 dB, and this is the cutoff frequency lower, this is the cutoff frequency higher, and this portion, middle portion, is called the mid frequency. It is called the mid frequency, and after that this portion is called the high frequency, and before that this portion is called the low frequency. Now you can easily see from the diagram that during this period gain is constant, but after that gain is reduces drastically when you go to the lower frequency and go to the higher frequency. So the amplifier gain is reduces drastically whenever we move towards the low frequency and the high frequency, and that's why there is two cutoff frequency, lower cutoff frequency and the upper cutoff frequency. These two frequency actually signifies that between this range the amplifier can be used as a constant gain amplifier. Otherwise, if we deviate from this range of this frequency, then our amplifier gain will not be constant. Okay, so the response, whenever we have discussed the response of any kind of amplifier, so that may be the time response. Time response is actually defined that the variation of the output with respect to time, and also this is the frequency response. So this is the frequency response. Okay, so this is the frequency response, that is the plotting or the variation of the output or the gain. Output or gain, that gain is nothing but output by the input. So if we plot the gain, so that will also signifies that the variation of the output also. So frequency response is the variation of the output or the gain with the frequency of the input signal. So that means if this is the frequency of the input signal, the frequency of the input signal changes, then the gain is not fixed. That is the main aim of this study of this frequency response. Okay, till now we have not discussed that what is the source frequency. We have not considered the or bother about the source frequency. We have not mentioned that what is the frequency of the input source, and we have calculated the gain, and we have assumed that the gain, this gain is fixed throughout our range of the frequency of the whatever may be the input signal frequency, that gain will be fixed. But that is not the case. From the diagram you will easily identify it that if we change the input signal frequency, then your amplifier gain will be change drastically. But for a certain portion of the frequency, that means between FL and FH, that means the lower cutoff frequency, and the higher cutoff frequency gain will be fixed. So that is our concern. So that is also called the midband gain. So that is the highest gain. So midband gain is the highest gain. That you also remember that the highest gain can be achieved into the midband frequency or the midband gain. That is called the midband gain. So that is all about the frequency response, why we study the frequency response. Okay, so next the term 3 dB, and what is the meaning of this lower cutoff or the cutoff frequency. Okay, what is the meaning of the cutoff frequency and this 3 dB. Now whenever we discuss the gain in dB, okay, so whenever we discuss the gain in dB, then in decibel, and that can be represented as 20 log with base 10 into this voltage gain. So voltage gain is nothing but the now this voltage gain, this is the voltage gain, that means the output voltage divided by the input voltage. Now suppose, what do you mean by the cutoff frequency? I am here going to discuss this cutoff frequency. Now in the case of the now in the case of the cutoff frequency discussion, suppose this gain we have a maximum gain. So maximum gain is defined by this is your maximum gain. Suppose we have assumed that this gain is mx, and we have assumed that the gain is reduced by root 2. So gain is reduced by root 2 times. Okay, so the expression becomes 20 log 10 mx minus 20 log root 2. So this 20 log 10 root 2, 20 log 10 root 2 is nothing but your 3. So this is your 3 dB. If you calculate this will comes out to be 3. So this is your 3 dB. That means if the gain is your maximum mx, from there if you go down by 3 dB, then this intersection is known as your cutoff frequency. Okay, so this is the definition of the cutoff frequency. That what do you mean by the cutoff frequency? Why we goes the root 2 times lower than the maximum gain, and this is called as the cutoff frequency. So the 3 dB frequency, cutoff frequency, both are same, and this 3 dB frequency also can be equivalently called as the gain, maximum gain divided by the 2. Okay, sorry, the maximum gain divided by the root 2. Okay, so if your maximum gain is a, and if we divide by this root 2, so whatever may be this gain, so this is your cutoff frequency. This is equivalent to your cutoff frequency. We can get the cutoff frequency from the intersection. And also 3 dB is also the same term, cutoff frequency, 3 dB frequency. 3 dB frequency is the maximum gain divided by root 2. Okay, if we goes down the root 2 times, that will be your 3 dB frequency. So that's why we call the 3 dB frequency as the cutoff frequency. And also at this point, yeah, I will left you as a exercise that you will study that at this point, whenever your gain is down by root 2 times, then power becomes half. So the half power frequency, so if the gain is reduced by root 2 times, power will become half. So the half power frequency, 3 dB frequency, cutoff frequency, all three signifies the same thing. Okay, so that is the all about the frequency response and the representation of the gain like this, and what is the exact mathematical definition of this cutoff frequency. Okay, so that is all about this. Next we discuss some of the capacitances. We will study what are the factors that is responsible. Actually what happens in the case of the AC circuit, whenever we have modeled the transistor with the help of the RE model, H parameter model, or the high bit pi model, then we have not discussed high bit pi model. we only consider the resistances and dependent sources to model the transistor. So we have not used any capacitor, any inductor into our circuit to model the transistor. Okay, so that is the disadvantages of this model, so that is not happening. Okay, capacitor and inductors play a very important role because here we have not considered the effect of the frequency. So whenever we consider the effect of the frequency, resistances and the dependent sources are not only important, in spite of that capacitor and inductors play a very important role. Okay, why? Because at the low frequency or the low power, you can say at the low power devices, capacitor play a very important role, or the capacitor study becomes very important. And in the case of the, that's why the electronic circuit, that means the low power circuit, we study the capacitances. Okay, in the case of the frequency response, but in the electrical circuit or the high power circuit, we consider the inductances, or inductor plays a very important role whenever the device is operated under a very high power. So the electrical circuit falls into this category, so that is a very high power devices. So that's why whenever we study the electrical circuit frequency response, then we will must include the inductor into our model. Okay, so that is all about the importance on capacitance and inductors. Next, whenever we want to study the frequency response, we have seen in the graph that after certain frequency or the certain portion of the frequency, gain is fixed, but after that gain is reducing drastically. Now we want to study what are the factors responsible for the reduction of this gain. Okay, we want to study what are the factors responsible for this reduction of this gain. So for that purpose, we will show some of the capacitances associated with the BJT. Okay, so the capacitances in BJT amplifier. Capacitances in BJT amplifier. Now what are the different capacitances we have assumed in the BJT amplifier? So I am drawing in the here that what are the capacitances involved in the case of the BJT amplifier. Okay, so if you consider that this is a BJT amplifier as a black box, or the BJT as a black box, then you consider this is the input voltage source. Okay, so we have considered this capacitance CC1 here, this is CC1. Okay, and this is your capacitances called as CD. This is your capacitances called as CT. Okay, and there is also in the output section there is a capacitance, all of you know that, this is called as CC2. Okay, and in the case of the emitter section there is a resistance, and across the resistance there is a capacitance, so that is called CE, and this resistance is called RE. So this model, all of you know that only the unknown thing or the unknown unknown capacitances comes here is your CD and your CT. Now what do you mean by this CD and what do you mean by this CT? So this capacitance, all of you know that along with the voltage source at the input section, this capacitance comes into picture, and this is the bypass capacitor across the RE. This is the output section capacitance. So this CC1 and CC2, these are called the coupling capacitors. So CC1 and CC2, okay, these are called the coupling capacitor. These two are called the coupling capacitor. Now the unknown capacitance, this is the bypass capacitor CE. Okay, bypass the RE, used to bypass the RE, and these are the some of the reasons. So this CD between the, this is, suppose this section is base, collector and the emitter. So between the base and the emitter there is a capacitance. So base and emitter are the forward bias. So if you study the diode, then you know that in the forward bias of the diode there is a diffusion capacitance exist. So that is your diffusion capacitance, that is internal to the device, and collector and the base junction is reverse bias, and whenever the diode is subjected to reverse bias, then there is a capacitance exist, that is called the transition capacitance or the junction capacitance. So that is represented by this CT. Okay, so these two capacitors are the internal to the BJT. Okay, so I am again repeating, the base and the emitter junction. Okay, your base and the emitter junction is forward bias. So that means whenever your diode is in forward bias, then there is a capacitor exist. That capacitance is called the forward bias diffusion capacitance, and whenever the diode is subjected to reverse bias, there is a capacitance exist. So that capacitance is called your transition capacitance or the junction capacitance. So that is represented by CT. So these are the external capacitance CC1, CC2 and CE. These three capacitances are called the external capacitances. Okay, and the CC1 and CC2 are the coupling capacitance, and CE are called the bypass capacitor. Both three capacitor are the external to the transistor. Okay, we are externally connected this, but this CD and CT, these two capacitances are internal to the BJT and arises due to these two facts. Okay, so that is all about the capacitances inside the transistor. Okay, next we will study why does gain reduces at low frequency. So why does gain reduces at low frequency? What are the factors responsible for that? So at low frequency what happens, that CC1 CC2 actually dominates. So this value CC1 CC2 and CE, both the three capacitances actually dominate. The value of these capacitances in microfarad range, so these are considered as very high value. Okay, generally the reactance offered by a capacitance is 1 by omega c. Okay, so at low frequency, at low omega, this value is actually high, so we can consider this value Xc as moderate, so that we can consider these capacitances. Now as we consider these capacitances, reactance offered by these capacitances are moderate, then what happens, the voltage drop happens across CC1 CC2. Okay, so for that purpose your V0 reduces, so that's why as the V0 reduces, your gain is also reduces. So that is the factor that why the gain is reducing at the low frequency. And there is another factor, that this emitter bypass capacitor that is used to bypass the resistance at the emitter section does not completely bypass RE. There is some sort of reason. Okay, completely bypass RE, it will be not able to bypass completely RE. So that's why RE is responsible for the negative feedback. So as the negative feedback happens, if it does not able to bypass the RE completely, so negative feedback actually exists into the circuit, and for that purpose gain is reduces. So these are the two factors responsible that why gain is actually reduces at low frequency. Okay, so next we will consider the different frequency range of the capacitances, that capacitances we have discussed, and what capacitance we can consider and what capacitance we do not consider at different frequency. So the frequency range and their capacitances. So at the low frequency, there is a coupling and bypass capacitance, there is a range, coupling and bypass. Okay, and next is your parasitic capacitance. Parasitic capacitance is inside to the device. Okay, inside to the device means that is the CD and CT. So a lower frequency, and next is your mid frequency, and next is your high frequency. So what frequency, what capacitances we should consider? So in the case of the and the value of the coupling and bypass capacitances is high, its range is microfarad, and the parasitic capacitances value is low, it is in the range in picofarad, that you must consider. Okay, so at lower frequency what happens, actually reactance offered by the capacitance is 1 by omega c. Now at low frequency we can consider these coupling capacitances. We can consider, why we can consider, because your omega is low, so xc equal to 1 by omega c, so your omega is low but the capacitance does not low, capacitance is high, so this value is moderate, so that we can consider this value. That's why we have written that we can consider this value at low frequency, but this parasitic capacitance is open. Why this is open? Because this value is low and the parasitic capacitance's value is again low, so this value is very much low, 1 upon this is very much high. So if this is very much high, reactance offered is very much high, or the resistance is very high, then you can consider this will be as open circuit. So that's why it is written as open. So at the low frequency we can consider the coupling and the bypass capacitance, but we cannot consider the parasitic capacitance. Likewise, in the same reason, in the mid frequency range we can sort this coupling and the bypass capacitance, and this can be considered as open. So this is the condition we have considered. Whatever analysis we have studied till now, this is the condition we have assumed. We have not considered the low frequency and the high frequency, we have considered the mid frequency. That's why we short circuit the capacitances always in the case of the analysis, AC analysis, and the coupling and the bypass capacitance we are going to short circuit because this reason. Okay, and in the case of the high frequency always you have to short circuit, and you can have to consider this capacitance. You have to consider this capacitance. This capacitance you cannot say that it is open, you have to consider this capacitance. So whenever you want to analyze the transistor at the high frequency, then you must consider, consider this parasitic capacitance that exists inside the Bjt. Okay, so next, the response of the Bjt at low frequency. So actually whenever we want to discuss the Bjt response at low frequency, so the low frequency response of the Bjt actually looks like a high pass filter. So this is the response of the Bjt at low frequency. Okay, so this is the response, this is actually the response. So if you know the filter, then you can see that this is the response of a high pass filter. It actually passes, this is the gain, this is the frequency, so it actually passes all the frequency at high frequency, but it actually blocks all the frequency. That means the gain is low, that means it actually blocks all the frequency at low frequency. That's why it is called the high pass filter. High pass filter means it passes all the high frequency and blocks the low frequency. So that is the response. The response is actually looks like low frequency response of the Bjt. If you consider the low frequency response of the Bjt, the low frequency response of the Bjt actually looks like the high pass filter. Okay, like the high pass filter. Now in the passive high pass filter, I don't know if I have studied or not, but the passive high pass filter actually looks like this. So we will analyze the passive high pass filter circuit and try to derive a equation, and whenever we study next the Bjt amplifier, we will equivalently look into the circuit, look into the equation of this circuit and try to match the parameter with the Bjt, so that we can easily identify what is the cutoff frequency. So we will study this is, so this is a high pass filter circuit, passive high pass filter circuit that we are going to analyze. Okay, so the response of this high pass filter circuit is actually the same. That's why we are analyzing this circuit, because I have said previously at the first that the response, low frequency response of the BJT looks like this. So this is nothing but a high pass filter, and this circuit is nothing but a high pass filter. So that's why next we are going to study the high pass filter. Now if you know the transfer function, if you know the transfer function concept, then all of you know that the transfer function of this circuit is V0S divided by VIS. This is nothing but R divided by R plus 1 by SC. Okay. I advise you to study this Laplace transform so that you can know this. Okay. So if you just solve this, this is SCR divided by 1 plus SCR. This S is nothing but J omega. Okay, this is the Laplace parameter or the operator. So this is the transfer function. So this is nothing but your gain. So your gain, if you replace the S with J omega, so this is J omega CR divided by 1 plus J omega CR. Okay, now if you want to gain in mod value, only the mod value of the gain, then it will be nothing but omega CR divided by root over of 1 plus omega CR square. Okay, so this will be nothing but 1, if you simplify it further, 1 divided by 1 plus 1 divided by omega CR square, and if you further simplify it, it will be 1 divided by 1 plus omega L divided by omega. Omega L is your cutoff frequency. Omega L divided by omega square. Okay, so from there you can easily say that from this equation, I am writing the equation. So gain, all these two equation, 1 divided by root over 1 plus omega CR square. Now from there is at omega tends to infinite, what will be your gain? At omega tends to infinite, this term will be 0, so gain will be nothing but 1. So you can see that the gain is nothing but 1, high gain. Okay, maximum gain. At omega equal to 0, your gain is found to be, so if it is 0, so 1 divided by 0 infinite, so gain will be 0. Okay, so this is the characteristics of the high pass filter. I advise you to study the high pass filter. So high pass filter characteristics is something like this. So you block all the frequency, and after that it passes all the high frequency. So that is, you can see that the low frequency gain is 0 or very low, and the high frequency gain is 1 or the maximum. So that's why if you just compare this, this omega L, is comes out to be 1 divided by RC. 1 divided by RC, and at omega equal to omega L, that means the lower cutoff frequency, your gain equal to 1 by root 2. That we have already studied, that the maximum gain is 1, and whenever the cutoff frequency comes into picture, the gain is reduces by 2, reduces by or the divided by root 2. So that we have already studied. So that is the meaning of writing down gain is 1 by root 2. Okay, so if you want to write down the cutoff frequency is hertz, so FL, lower cutoff frequency, so 1 by 2 pi RC. At the cutoff frequency is 1 by RC, omega L equal to 1 by RC, and if you want to express this, actually omega L equal to 1 by RC, and if you can express it is F, then it is 1 by 2 pi RC. And the overall voltage gain, low frequency, is your, this is midband gain. So midband gain is highest. I have already said that the highest frequency is the midband gain. If you compare with the transistor, what will be your case? Okay, here the gain is, previously here the gain is here the gain is 1 divided by 1 is the maximum gain, so 1 divided by 1 plus omega L divided by omega, so 1 is the maximum gain. So here in the transistor I have said that the mid frequency gain is maximum, because whenever you study the transistor characteristics, so this will be your mid frequency gain. This frequency gain is highest, so that is represented by voltage gain at mid frequency divided by 1 plus omega L divided by omega the square. So this will be your frequency voltage gain at the low frequency represented by this equation. So we will see whenever we analyze the transistor with the help of this, or the transistor at the low frequency, and try to analyze the cutoff frequency, then we will must use this equation. So I will advise only to pay attention to this. The low frequency response of the BJT looks like the high pass filter. That's why we have studied the passive high pass filter circuit analysis and try to compare it with the BJT. Whenever we study the BJT, then we must compare it with this circuit and try to determine the cutoff frequency. That's why we have studied this. Otherwise this circuit is not important here, because this circuit is very much easy. So, and this circuit response is the same as the BJT, so that's why we have studied it and derived the equation based on this, and from there calculate the cutoff frequency. And later on whenever we will discuss the amplifier circuit and try to analyze or try to derive the cutoff frequency, then we will compare this with this equation and try to derive the cutoff frequency. Thank you.